Hi folks, Mr. Ackerman here. Thanks for watching. In today's video, we're going to be looking at how to do the lab for Unit 3, the one where we study uniform circular motion. Textbook page reference is 152 to 153, and if you want to find it in the course pack, you'll find it on page 7. There's a data table, although we won't be using the exact same data table, and also page 17 to 19 where you'll find the rubric, and that we will be using. So the basic idea in this lesson or this lab is that we're going to take the formula for centripetal force, we're going to rearrange it so it looks like this, and we're going to try to answer the question, does this formula accurately describe the motion of an object in uniform circular motion? So if I could summarize really quickly, is this, and by this I mean this equation, valid? Now that's not a very technical way of stating things, so maybe we could ask it a little bit more accurately. Does the theory, and that's this thing, agree with experiment? And so we've got to do an experiment to get some results, some information about an object that's spinning in uniform circular motion and compare. So let's see how that's going to happen. The apparatus that we're going to be using is described by this diagram. You're going to have a hollow tube, which in this case I have one, it's a glass tube with a protective rubber coating around it. There's a string that runs through it. On one end of the string is a rubber stopper like you'd find in a chemistry class, and on the other end is any sort of metal masses. I'm going to use some washers, like some rings, some metal rings that are taped together in groups to provide a little bit of weight. And what I've done in this lab, since we're not in school at this time, is I've done the lab at home and I videoed the different trials. And you're going to see those videos shortly to collect your own data while you watch. Here's a screenshot of one of the frames from the video, and you can see I'm holding the hollow tube in my hand there. You can sort of make out the smudge of the rubber stopper as it goes along. I drew a little circle on it to make it easier to see. That's the M in the formula that we talked about a minute ago. It's spinning in a circle, as you're going to see shortly in the video where you collect the data, and the circle has a radius. There's the string that's running down, and down here it's attached to those metal washers, the masses. The force of gravity is going to pull down on them, and what you're going to see me do is spin them at such a rate that the circle stays the same radius. In other words, you can imagine if I spin this thing too fast, the masses here are going to move up. The mass here, the rubber stopper, is going to move outward due to the fictitious force, if you can think about that. And I don't want that to happen. I want uniform circular motion. So I'm going to try to spin this at such a rate that the masses hanging here do not go up or down. So the instructions in the textbook tell you to put a little paper clip, or I'm going to actually use a piece of tape, somewhere just below the bottom of the hollow tube, and keep your eye on that so it doesn't go up or down during the rotation. That's the way you're supposed to know that you're spinning at a uniform rate. Now, I'm just going to move myself over here for a minute so that you can see everything. The measurements we're going to make then are for the centripetal force. We got to measure the downward force of gravity on these masses, because if we keep this stationary, that'll be equal to the tension force in the string, and that string will be providing the centripetal force. So we're going to put the metal washers on an electronic balance, and we're going to weigh them, and that, if we multiply by 9.8, we're going to get the force. In terms of the radius, I'm going to take, as you can see here, the rubber stopper at one end of the meter stick. I'm going to measure out a certain length of string to the top of the tube. That's the center of rotation. And I'm going to put a little paper clip down here, or a piece of tape, keep my eye on it, make sure it doesn't go up or down. Finally, the mass of the thing going in a circle, the rubber stopper, again can just go on the electronic balance. So let's see what comes next. When we start thinking about this, you're going to see that the formula has three letters, three variables on the right side. It's got a dependent variable here, the frequency is what's going to be measured. It depends on these variables here. But in a scientific experiment, I can't have 3 variables that are independent running at the same time. I can only pick one. So in part A of the lab, which is the one that we're going to do here, we're going to vary the centripetal force, but we're going to keep the mass and radius constant. So these are your constants. Of course, 2 pi is a constant, and this is going to be the independent variable. So basically, I'm going to be varying the amount of force and measuring how the frequency responds to that over several trials. If we were in school, we would also do part B, where we ask ourselves, how does frequency depend on radius? And we would keep the force and mass of the rubber stopper constant. And in part C, we would ask how the frequency varies depending on the mass of the rubber stopper, and we would keep the force and radius constant. But we're going to do this one today. So first off, I'm going to be measuring mass. I got to check if my scale is accurately measuring. So what I did was I brought home some standard masses. You may recognize them. We've used these in the past in class. Each one is guaranteed by the manufacturer to be 50 grams. So I put 1, then 2, then 3 on this electronic balance, and you can see they go out to 50 grams, 100 grams, 150 grams. That's telling me that my scale is calibrated and it's working properly. In terms of the radius, you can see here, we're going to be measuring the distance from the rubber stopper to the center of rotation, and if I just zoom in there, I don't know how well you can see, but this is roughly 45 centimeters. I stretched this out because when it's spinning it will be stretched out, and I put a little piece of paper near, or a little bit of tape rather, near the bottom, so I can keep my eye on that while I spin it and make sure it doesn't go up or down. Finally, the mass of the rubber stopper, the thing going in a circle, I measured that. It came to 14 grams, and I'll just show you that so that you trust me and we're ready to go. So let's look at the next step. We're going to do 5 trials, and for each trial, we're going to increase the amount of hanging mass. So I've already weighed these out, and I'm going to let you see what the numbers were, and you can record that. So first, there's 1 hanging mass, and we can see that there's 34 grams there. For 2 hanging masses, so now there's 2 of these cylindrical shaped masses, 69 grams. And as I move along here, you can see there's going to be 103 grams, there's going to be 137 grams, and the last one is 172 grams. Now what you need to do is convert these into force of gravity so that you know what the tension force is and you know what the centripetal force is. So of course Fg is equal to mg, and you have to repeat that going all the way down this table. And then what we would normally do in school is I would take this apparatus and I would start spinning it, but instead I recorded a video or a series of videos for you. So what we're going to do is that's going to get spinning, and I'm going to ask you on your own to take up the stopwatch on your phone, or if you have another stopwatch you can use that, and I want you to time 20 revolutions. Remember to start counting at 0. So in other words, as the mass goes around, pick a spot where you're going to begin and end your counting, and start off at 0, 1, 2, 3. When you get up to 20 and you have your time, you're going to record that in these spaces here. And then you're going to calculate the frequency. Remember, frequency equals the number of revolutions divided by the time it takes. So for example, 20 over whatever you had in here is going to go in there. And that's how you're going to collect your data. Each of you is going to have a different measurement, I'm sure. You're not going to share yours. You're going to do them all on your own by watching the video. And in that way, everyone's going to have slightly different results, which is what I expect. Let's take a look now at the trials. So the first trial is for the first hanging mass. I'm going to play it here. I don't believe the sound came through, but that's fine. You can begin timing whenever you're ready. All right, so that was the first trial. I got to say, it was a little bit weird for me to sit here for 30 seconds just staring at the screen doing nothing. So I'm going to move myself off the screen for the remaining trials. And if you're wondering, if you did hear the sound there and you're wondering who I was talking to, it was my son who was helping me to record. So I'm just telling him to start and stop the stopwatch. I'm not talking to myself. I haven't completely lost my mind. All right, here we go. Here is trial number 1 with, it actually says trial number 1, but this is hanging masses number 1 and 2. This is actually trial number 2 coming up. Okay, just a little note there. While I'm spinning this, I want to tell you a little bit about what it's like. Here, let me bring myself back in here. I want to tell you a little bit about what it's like because normally you guys would get to do this on your own, but you can't this time because you're not with me and we're not in school. It's not easy to spin this thing at a steady rate. You constantly have to give like a little push. That's unavoidable, but if you push too hard, it changes the frequency. So you got to practice and make sure that you do it just enough to keep the motion constant. The other thing is it's really hard to spin this thing in a horizontal circle, and I'm going to leave it to you to think about why it needs to go in a horizontal circle and should not be kind of on an angle. Try this at home if you have a little pen and you take the pen apart, you pop out the ends and remove the ink and all that, put a string through it and just tie something to the end and try spinning it. You'll see it's not easy. So later on in the lab, you have to make some recommendations about how to improve the lab. That's part of your mark. And so I'm just telling you some of the things that I've experienced so that maybe you can think about that and make comments in the recommendations section, which we'll get to in a moment. Anyway, enough of me. Let's go to trial number 3. 3 hanging masses. Here we are with trial number 4, 4 hanging masses. And finally, trial number 5, all 5 hanging masses. Okay, so now you should have your data. You should have this entire table filled out. And what do we do next? At this point, you're going to go to Microsoft Excel. You're going to create a data table. From that, you're going to create a graph. And by playing around with some of the tools in Excel, you're going to get the experimental result, which is going to be an equation that Excel is going to provide for you. And then we're going to compare the experimental equation with the theoretical equation that we talked about earlier in the video. So let me take you to Excel and show you what that looks like. Now, warning, sample only. I made these numbers up. They're not real, okay? So do not use these. I hope no one hands in these numbers. That would be very, very bad. You've got to get your own data. But anyway, 5 trials, 5 imaginary masses. The force has been calculated using mg. Keep in mind this is in grams, not kilograms. I made up some times for 20 revolutions, and I calculated the frequency. Now, here's the graph, and here's the experimental equation, but how did I get that? First thing you're going to do is you're going to find your x values, your independent variable. So that's the force here. You're going to click and drag all 5 data points. Now, go to your y values, your vertical axis, your dependent variable. On a PC, hold down Control, click and drag. On a Mac, hold down Command, click and drag. So click and drag. So now you got both columns highlighted. First the x's, then the y's. Then you're going to go to Insert. You're going to find this little icon. Go to the scatter plot like this, just this one. And it's going to create a graph for you. Now, I took the time to write sample only, frequency versus force. I labeled the axes because I wanted you to see them. You don't need to do this because I'm not asking you to hand in the graph. All you need to do is click on one of these data points, and they're all going to get highlighted like this. And then you're going to go Add Chart Element, Trend Line, More Trend Line Options. And that's going to pop up over here. Let me just move myself over for a minute. And you get a choice of what kind of equation you want to use. Should it be linear, logarithm? I don't know. You could try all of these, but actually I have a better answer for you. First, I'm going to tell you what the answer is. The answer is to select power, and then scroll along and click this, Display Equation on Chart. And then what you're going to see is, magically, on the chart, you get a line of best fit, and you get the equation. I'm just going to X this out. You can see the equation here. Y, or frequency, F equals 2.1791, X, which really means force, to the 0.4283. That's the same thing that's here. You can double-click and highlight that, and right-click and go to fonts, and you can make it bigger if it's too small to see. All of those rules that you normally use when you're typing still exist, but that's basically how to find the answer. Now, question. Why did I choose power and not some other curve? The answer is that when we take a look at the form of this equation, it has the form that Excel calls a power curve. It's got a variable, kind of like y equals, and then it's got 1 over 2 pi as a number. Remember, MR, these are constants, so they make a number. So you basically have 1 over 2 pi root MR times FC is the variable. That's like x. And it's raised to the half power because it's a square root. So constant, that's like y equals ax to the n. And this is what Excel calls a power relationship. That's why we chose that, okay? Now, our job is to figure out what was this constant supposed to be. I can see what the exponent was supposed to be. It's supposed to be a half. Let's look at the exponent for a minute. This is the theory. How well did we do in my fictitious data? I have 0.4283. 4283. So you can see right away I'm off by about, this is like 42, 43, I'm looking for 50. I'm off by almost 15%, not great. What about the constant here? Well, in this lab, what did we have? Let's do 1 over 2 pi times 1 over the square root. The mass was 14 grams. You've got to convert that to kilos. And the radius was 45 centimeters. You've got to convert that to meters. So let's take out our calculators and figure out what that comes to. I've already got it calculated on my screen, and I've got 2 to a couple decimal places. Okay? It's actually 2005. So let's go back to Excel. This one said 2.179, 2.18. So, okay, under 10% is how far off it was. Not bad, not great. Okay, kind of just okay. Anyway, you're going to take your own data and see what you can get. So let's go back to where we left off. I think we stopped. We're going to continue here, rather. Compare these. So your theoretical, we had, let's say we had frequency equals 2.00 centripetal force to the 0.5 versus the experimental, which is going to be this. Now remember, this is the fake data. Don't use this number, okay? You've got to take your own. 2.18 to 2 decimal places, and FC to the 0.43 to 2 decimal places. So what I'd like you to compare at this point is, how does the coefficient compare? And as you know, we're going to use a percent error. And then, how does the exponent compare? Again, use a percent error. And in that way, we're going to get some idea of how close we got to the theoretical result. Okay? Finally, how are you being marked? What am I looking for you to hand in? If you go to course pack page 17 to 19, you're going to see your answer. So let's go there now. I'm going to open this up as a PDF. We're in the Unit 3 course pack. I'm going to jump down to page 17, and here we are. You are asked to hand in only the following items. 1, something called an abstract section, which I'll explain in a moment. 2, a conclusion. I'm sure you've heard of that before. 3, a recommendation section. And finally, your data table and calculations. Now, the data table and calculations, if you want to write them out on paper and photograph them and import them into your PDF, like add them as an image, you can. Or you can just type them, which I think is probably the better way to do it, and you're going to put those into a Word or Google Doc, and then you're going to download it as or save as a PDF. But in this section, that's where I know you did this lab. And that's how I'm going to know that everyone did their own lab and didn't share data. So I need to see this. You got to include this. I'm not marking this part, but I will not mark your lab without this included. So make sure it's in there. Okay? Let's go back to the abstract section. What is an abstract? Basically, an abstract is a very brief summary of what's included in the lab, and it lets the reader know whether he or she should continue reading. Think of it as a quick cover letter for a resume when you apply for a job. The job recruiter is going to take a quick look at your cover letter, and if it looks like you've got the skills that he or she is looking for, you'll go and read your resume and maybe you'll have an interview. If you can tell right away that it's just not right, it's going in the garbage bin. And we don't want your lab going in the garbage bin, so you have to write a good abstract. What is in there? Basically, you got to tell me what was done in the lab. Tell me what its purpose was, and briefly describe what happened. So what did we do here? We were studying uniform circular motion, right? What did we do? Did we drive a car in a circle? Did we spin a ball around the inside of a cylindrical tube? Describe briefly what we did. What were the key results that we obtained? What were we trying to do? Go back to your objective, which is down here, and then think about whether we got our results to mesh with our objective. Did we answer the question we set out to answer? What are the key conclusions that were made? Well, if you think about it, we had this objective, and we guessed, theoretically, there was a certain equation, and then we checked it out experimentally. So you tell me, how close did we get? What were the results? Maybe you should show the actual equation that we got and compare it to the theory that you were looking for. So that's the abstract section. If you click on this link down here, it'll take you to a website I once found which gives a pretty good idea of what's meant to be in a lab report for a university prep level. Scrolling down a little bit, here's just more of a description of what I just gave to you. And if you go even further down, they write an abstract for an experiment about something called Hooke's law. If you've ever learned a little bit about springs, Hooke's law describes how springs stretch when you apply force to them. Here's an abstract. Look how short it is. Really, really brief. Here's another one, also very brief. It's not a lot, it's just enough to let the person who might read your lab report know whether he or she should continue reading. And it contains all the things that are mentioned in here, or that I mentioned in here. Okay? Next up, conclusion. Include a conclusion, please. What do you do here? Refer back to the hypothesis and comment on whether it was supported by evidence. What's our hypothesis? Did we even mention the word hypothesis yet? Well, I don't think I mentioned the word exactly. However, if you think about it, we had a theoretical result we were expecting. There's your hypothesis. You think this is what uniform circular motion looks like. Did you get it? And what's your conclusion? If there were disagreements between the results that you got and the theory, or your expected result, summarize them. Don't give me a rundown that lasts pages. This should be brief. Summarize the key reasons for disagreement. Finally, tell me why you think these results are important. What is the significance of knowing about uniform circular motion? And what could someone do with these results once they're obtained? Like, what would be the next step? Something new or more advanced to investigate? Or how could these results be applied in the real world? So there is your conclusion, not long. Finally, the recommendation section. Here's where you go and you make recommendations for improving the lab. They should not be elaborate. Please don't say something like, air resistance is a problem, so we recommend doing this lab in outer space. The Thornley space program is no longer running. We don't go up into space where there's no air so that we can do the experiment without air resistance. We don't have the money or the resources, so that's not a good recommendation. But maybe you can think of a recommendation that maybe controls unwanted forces in a more practical way. Maybe you're going to take a pen in your house and you're going to spin this thing around, a mass on the end of a string, and see what some of the challenges were that I had to deal with, and that'll give you some hints about what recommendations to include. I've got a few hints for you here, and you're more than welcome to take them or leave them. Think about unwanted forces and how we might solve for those. In other words, how we might remove them as a problem or deal with them. If it's tough to rotate this thing, to keep it horizontal or to do it at a steady pace, how do you recommend we do that? What's your solution? If there were any problems with measurements that you can think of, any challenges, you measured a number of things here, give me some solutions. Okay? And that's basically it. Pay attention to the rubric. I'll finish with that. The rubric is further on in the course pack on page 18 and 19. The abstract should be about a third of a page, not very long. It's going to get you 5 marks for communication if done according to these criteria in here. The conclusion, also about a third of a page, 5 marks for communicating clearly, and 5 marks for your thoughts and ideas, all of which are summarized here. And finally, the recommendations. This might be a little bit longer because you might have several recommendations, about half a page maybe. Communication, got to be clear, 5 marks, and thinking for the quality of your ideas right here. All right, I hope this lab works out well for you, and I'm sorry we couldn't be doing it together, but this is the next best thing. Thanks for watching, guys. Looking forward to seeing your reports. Stay safe. See you soon. Bye-bye.